In this lab, we observed the motion of an unknown star as it traveled along an orbit around a black hole. My task was to evaluate this data given and discover the mass of the black hole with the aid of a computational model. Initially, the only data given was the mass of the star, the location of the black hole, and the location of the star at each time interval. With this given data, I was able to evaluate the velocity at each time interval, and with Newton's second law, I was able to derive the net force acting on the star. This force value could then be inserted in the universal law of gravity, through which I could determine the mass of the black hole. For this lab, our unknown is not the motion of the objects in question, but is the value of the forces acting on the objects. In the given .csv file, there is a list of coordinates which describe the star's location relative to an arbitrary origin given in the problem statement. The black hole is stationary, located at the point 0, 4 times 10 to the 10th meters. The problem statement also gave an indication for the time interval, which was 1 day, or 86,400 seconds. To find velocity, we will need to evaluate the change in the star's position in relation to the change in time, delta t. Due to the large amount of data, we will use a written code to help evaluate these values. Here's the code that creates a computational model of the star's movement around the black hole. As you can see, I used different arrows to represent the parallel and perpendicular components of the momentum. The purpose of these values will be explained later on as we discuss the method behind computing the force components. Within the code, we represent the change in position by this line. Essentially, this is just the computer's way of taking the star's x value at one moment in time and subtracting the value by its previous x value. To evaluate the x velocity at that moment in time, I wrote the line x velocity equals delta x over delta t, which is the same as taking the change in position along the x direction and dividing that value by the change in time delta t. This same procedure is done with the y coordinate in order to find the velocity in the y direction. To compute the velocity of the star, we must first represent the final and initial velocities at any given time using these lines of code. Since momentum is simply the velocity times the mass of the object in motion, we can represent p initial and p final by taking the star's mass and multiplying it by the initial velocity and the final velocity, as seen by these lines here. Earlier we stated that the velocity would be used to evaluate the force. In order to accomplish this, we must first acknowledge the relationship between force and momentum. Momentum is a vector quantity that is evaluated by multiplying the velocity of an object by its mass. By observing the change in momentum in relation to the change in time, we can recreate Newton's second law of motion. Through this law, we can observe the following relationship. F net parallel plus F net perpendicular equals delta p parallel plus delta p perpendicular. Essentially, the perpendicular components of the change in momentum of an object is equal to the perpendicular component of the net force acting on that object. The magnitude of the perpendicular component of the change in momentum describes the extent to which an object is turning when it is moving. The magnitude of the parallel component of the change in motion, or change in momentum, describes whether an object is speeding up or slowing down. This information is essential for finding the force acting on the star, and in turn discovering the mass of the black hole. The line dp dt equals delta p over delta t describes the change in momentum versus time. To find the parallel component, we simply multiply the magnitude of dp dt by the direction of the star at that given time, which can be represented by this line. Since we do not know the value of the radius of the circle along which the star is traveling, we must evaluate the perpendicular component of momentum by subtracting the parallel component from dp dt, which is represented by this line of code. The most essential part of this code is this line here, which equates the net force to dp dt. At the bottom of my code, I placed inside the print statement the magnitude of the net force. As you can see, when we run the program, we see a simulation of the star traveling around the black hole. And in our print statement, we have this value, which represents the net force acting on the star. We now have a calculated estimate of the net force and can calculate the mass of the black hole. Using the universal law of gravity, we can insert our own known values and solve for the mass of the black hole, which is evaluated to be roughly 3.17 times 10 to the 31st kilograms. One important aspect to keep in mind is that the parallel and perpendicular components of the force are different than those of the momentum because the momentum components describe to what extent the motion is changing, whereas the components of force describe what is causing such motion change. If the black hole observed in this lab was replaced with a new black hole that produced the same results in terms of the star's motion, then there would be no way of determining the difference between the two black holes. This is because the star's motion was the only information used to find the mass of the black hole. And if this motion is unchanged, then for all extensive purposes, the black holes are identical. In conclusion, we can use the momentum of a moving object with Newton's second law to give a more in-depth analysis of the motion of that object.